Hello everyone, so this is our work for the TMLR Submission 2023. The name is Graph-based Multi-ODE Neural Networks for Spatio-Temporal Traffic Forecasting. The authors are Zibo Liu, Parshin Shojaee, Chandan K, Reddy, and they are all from Virginia Tech. So traffic forecasting is one of the key applications of spatial-temporal forecasting. It is really challenging due to one, intricate and extensive dependencies in traffic networks, and two, frequent non-stationary events such as traffic peaks or accident. Look at this figure. On the left figure, it is the traffic connection map, and on the right, there are the traffic road networks temporally, and in each time step, it has the traffic recording points, the roading network, which is the edge. And also in the bottom, it has the temporal part. However, it has some limitations. For example, the existing works use GNNs for road networks with graph structures, but they are facing the oversmoothing in deep architectures. Recent methods use GNNs plus residual connections or the neural ODEs to solve this oversmoothing problem. However, they also have some limitations of these previous Graph-ODE modules. Number one is they focuses on global temporal patterns but neglect local patterns. Number two, the absence of the dynamic semantic edges in the module architectures. Here we propose the solution, GRAM-ODE. It takes multiple connective ODE-GNN modules to capture complex local and global dynamic spatial-temporal dependencies. So this is the overall figure of our model. It has the A, global ODE module, B, local ODE modules, C, dynamic semantic edge ODE modules. Within A and C, it has the shared weights, which is number one technique. And within the local and global, it also has a constraint. It is a number two technique. Here is the experiment datasets. We use 6 PEMS and the metro LA datasets. And number two is the evaluation matrices. We use MAE, MAP, and RMSE. So here is the main results. We can find out our model reached the SOTA among the 6 datasets, except that one of the STF-GNN, which is slightly worse than that. Here's the ablation study. We use 2 datasets, PEMS03 and PEMS08. In each figure, we add the links one by one. For example, plus C is the add the edge ODE modules. Plus L, we add the local ODE modules. Plus shear, we add the shear weights among the global and edge constraint. Is the constraint between the global and local, and also the aggregation layer, the residual connection, and the GRAM-ODE, which is our model. It achieves the best performance. When we are adding the techniques, the performance getting better. So here is the efficiency and scalability figures. On the left, we compare the performance and the inference time. Even if our model has the longer inference time, it has the around 2% improvement around the STGODE. On the right, we compare this that size and relative gain. We can find out when the dataset is bigger, GRAM-ODE is getting better performance. We also compare the robustness between the GRAM-ODE and the STGODE. We can find out even if the noise proportion is getting bigger, our model still remains steady. Even if we are facing the largest noise proportion, say 0.4, normal distribution 0.4, our model still can beat some baseline models. So here's the conclusion. We propose the solution GRAM-ODE for spatial-temporal traffic forecasting. We utilized multiple coupled ODE-GNN blocks for improved representations. It outperforms state-of-the-art models in 6 real-world datasets. And also, the ablation study highlights the effectiveness of each component and demonstrate the robustness and scalability to input noise and larger datasets. Our code is open source on the GitHub. Thank you.